我讲一下怎么，比如说这个算法呢，算法的秘密就是说呢，这就是有名的 Shor algorithm，那它的秘密就是说，它全部都是 classical 的，只有中间这一段就是给一个数字 a 或者给一个数字 x，它可以找到一个 order r。对，因为可以讲这是一个神奇的事情，就是你给一个数字，比如说15嘛，然后 x 是2，我就可以找到一个数字叫做4，使得2的4次方16除以15/1这样。所以它的厉害的地方在于说，你给我一个 n 很大，这 n 可以超级大，1000个 bit，但是我不需要 exponential 那么多个数字，exponential 那么多个16，我就可以找到一个神奇的数字叫做 r10这个式子。一旦这个式子成立，我就可以使用数论的方式得到它的分解这个大的。如果我得到了这个 r 的话，所以神奇，所以这个所以 Shor algorithm 这个东西，它本身其实是数论的一个结果 number theory 的结果，只是它有一段它有一段是需要靠 quantum 去帮忙的点在于 quantum 可以找到 r，可以使得就是这是一个神奇的事情，这个 n 是超大数字，可是你不需要，所以 r 也是 exponential 这么大，超级大数字，可是你却不需要你。找到这个 r 却不是一个一个式，而是用某一个神奇的方法，可以让你直接得到一个 r 的这个等式是成立。一旦成立，你就可以做分解这个大整数。那例子就我刚刚讲的，就是这里小小的简单的例子。所以整个 Shor algorithm 的奥秘就在于说，它这一步是怎么做到的？这个大家可以想象一下，我给你一个周期函数，这个周期函数的周期是指数型那么大，可是我却不，可是我得到这个周期函数的周期，却不是一个一个去试它是不是周期。大家知道为什么？比如说，假设我就先设周期是一嘛，我就看周期是不是一，周期不是一，我再设周期是不是2，它周期不是我设周期是不是3，它不是这样，它有某一种方法可以不经由这样一个试，可是得到周期。这大概是这个东西比较直观的解释。到底怎么得到的？大在问，大家问。是不是就是一跟 B？没有，我这边写的时候写的不太这两个12，对，这两个值数应该是说你要算这个数字跟它的，对啊，它基本上来讲，如果它成功的话，这个就是 B，这就是 B。如果它成功的话，不成功就是说这个可能算出来之后跟它还是不会得到。你就在讲这个数字是 P 啊，基本上是，那 GCD 完之后基本上是，只要在除上要除到它而已，所以它会得到一个 trivial private。OK，那so the idea is that we need to find this quantum parts. So the mystery of this quantum parts is that how can I find I know n is exponential large. Right, so in order to solve this equation, I cannot try one by one. I cannot try a squared, a cube. And the check and because a is exponential large, right? So r will be exponential large. So the mystery is that quantum algorithm has this quantum computer. Quantum computer has a weird power such that you can find the period of the periodic function even when period is exponential large. So this is the key. How can I find r but not try one by one? Okay, so the idea is that using so-called basically it's Fourier transform. Okay, so let me define a so-called quantum Fourier transform. Over Zn, so n is you can view n is so n you can view n is 2 to the power of 2. But it's defined in general n. Okay, so definition. So this is small. So so this recall let me just recall so-called classical Fourier transform. So when you I think everyone heard of Fourier. Okay, stop. But it's just some table. Just that you recap your undergraduate or whatever. So everyone knows about Fourier transform, and so there are like three versions. The first version is that here, here, just one, maybe. Okay, so there are three things. I mean actually, one is called Fourier series, one is Fourier transform, and one is this one called basically is so-called classical Fourier transform, or simply a discrete Fourier transform. So we are talking about the third one. It is you can put it in computer science version of Fourier transform, or the discrete one. And the Fourier series, I think everyone knows, you have a function which is periodic, then you can turn into you can view this, you can write it as a sine cosine. But these are continuous variables. But now we are working in a discrete variable, right? We are working number fields. So everything is discrete. So classical version for the discrete version for definition is that give you a vector x0, x1, x capital N minus 1 is a complex number, and you map another vector by the 6. Because x to the j, the omega a to the minus 1 jk. Actually, you can use your cos 1. Okay. And then divide by 1 with square root n, and then this omega is the n roots of unit. Alright, so simply speaking, you just define your yj or yk or yk. The whatever square root n, just your xa, the omega a jk. Yeah. And sum over all j. Alright, over all the. Okay. This is already known in the computer science. It's so-called discrete Fourier transform. And then we just mimic into the quantum version. We say that, oh, if I have a vector x, let's say n is a power of 2, then I can write in terms of bit traces, like 0, 0, 1, 1, 0, 1, 1, then I can write x in terms of summation of some j, with j equals 0 and minus 1. And there are coefficient, I do this x, that's a coefficient of this, say x. And I can create another quantum state if I apply, but this is definition, right? Once I apply this quantum Fourier transform, then I get another vector here, and each yj change using a discrete Fourier transform. So this is the definition.
So can you remind me of the definition for the continuous case?
Oh, yeah. So let me okay. So let me what is going on.
Was like the interval.
Yeah.
The function times e to the power.
Yeah. So simply speaking, so in this case, then you have some function which is periodic, let's say 2 pi, let's say whatever c, and you can compute, and so this is periodic, right? So it's all this f is can be viewed as you can expand it in terms of something like this, and you can compute it as coefficient. Let's say, for example, Cn is 1 over 2 pi, and f of theta is pi n c. This theta from 0 to 1. You have changed this. So this is the series version. And for the continuous version, just do the integration. Just do this one to omega. I mean, by the way, if you know, I will explain the later of this chapter. If you know the group theory, so-called group representation, then you can unify all these Fourier transform maths into one simple framework. So what I'm saying is that if you go very high in very abstract mathematical way, so-called group representation, then you can combine three of that into one. But now it's not obvious. These three are the same.
So wasn't there like factor 1 over 2 pi somewhere, or is it for the reverse?
Yeah, this is just for reverse. This is just for the There's always on the quantitative constant.
So why is it built in? I'll write it in the.
Even here, yeah, actually there's a 1 over square root of pi. So
Okay, yeah.
Yeah. But in this case, it's 1/√. I will explain why this is 1/√. Okay, so this is a discrete version. Yeah. So it's really clear. You just divide a vector x and you just change xj to yj. A definition. Oh wait, so maybe this one is hard to remember, but this one should be this one is easy. This one is that when x is the basis state. Basis state meaning that x is a discrete like 0, 1, 1, 0. The x and the basis, then you just add each x to the just put x on the exponential x through k is over a and 1/√. And it extend linear. So if you give me any state, put your sum over x, and I'm just using this. Okay, so this is the definition. This is so-called quantum Fourier transform. It's basically the same as classical Fourier transform, right? But just change it as a view as a coefficient. So one immediate question now is that quantum Fourier. Remember we talked about quantum circuit, right? So one important thing in the quantum circuit is that we are only allowed to use unitary. So I define weird map. Whether this weird map can be implemented in the unitary in the quantum circuit. Right? In order to please, this guy must be unitary. So my claim is that quantum Fourier transform is a unitary map. And why this is sure? Here. Why is it? Right, because I still not I'm not yet tell you why this quantum Fourier transform this quantum Fourier transform is useful, right? But yeah. Yeah.
So wait, is the inverse formula for the inverse transform exactly the same? Or
so it's the unit there's y. The exponent.
there was a plus on the original.
Yeah, but in quantum that we define transform to be no plus, but the inverse has a minus. It's fine. Yeah, it's basically this convention.
Know what I mean? Can you go back to the slide? Because in the Oracle formula there's a minus.
Yeah, but this is the classical version. It's just in the classical version sometimes they define minus. Yes, this is fine. Just remember that whatever you do, you need to add if you define the transform to be plus sign, then inverse must be minus.
Yeah, okay, because for the classical one, it's 2 times minus.
Yeah.
So it should be minus that plus.
Yeah.
Okay.
That's fine.
Otherwise, it's the same.
Yeah. So this is interesting when you do like Fourier transform, right? When you do a transform here, if you define your transform to be exponential I omega t, when you define inverse, you need to do a negative, right? Yeah. It's similar as the series one. So you need to change this to be if you recover it, you see what I'm saying. So if you write your f in terms of summation Cn is exponential I s theta, something like that. If you expand your f in terms of plus sign, then when you write a transformation, there must be a minus. Then it would be consistent. If you define this to be minus sign, then this must be plus. So the only difference is that whatever you can define inverse, and you just need to define your inverse and the transformation. Just remember there's a minus. Okay. So now this is my Fourier transform. So I will claim the following. Quantum Fourier transform is doable. It's unitary map. It's unitary. But before we do this, before I do this calculation, I need to talk about one very simple identity. This is so simple. So this is very simple. This identity. Let me see. So what if I compute it? So J is a number, K is another number. You can J, K are integer. I compute omega n J. K is actually J from 0 sum over n minus 1. What is this? This is just omega n to the it's just 1 plus omega n to the K plus omega n to the 2K up to omega n to the n minus 1. Okay, so this is geometry series. I can compute for them. I know it's 1 minus A to the number of terms. But this formula is true if only if this guy is not 1. If this guy is 1, then it's ill-defined. So simply speaking, if yes, let's see it. Right? So if K is multiple of n, then you get 1, 1, 1, 1, you get n. Right? Okay. If K is multiple of n. Right? Because this is 1, 1, 1, 1, 1. Otherwise, this is not 1. But this is omega n to the K to the n. So it's 1 to the K, which is 1. So it's 1 minus 1, which is 0. Good. So simply speaking, this is non-zero. This is n. This is non-zero if K is multiple of n. Otherwise, it's 0. So should be like yes. It should be this. Okay, so you remember this one. Okay, so now we can prove quantum Fourier transformation is unitary. Maybe. So yeah, so basically the intuition is that when you do this omega to the power, then you are actually write a vector which you can view this omega as a complex number. It's a complex number, right? So we can view it as a vector on the plane. So if there are not the power, if n are not a multiple of n, then they will spread in all directions. And when sum of them becomes 0. Obvious. For example, if you take a 5 root of unity, for example, if you do this, you can view that, oh, this is 1, right? This is omega 5. It's here, 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 here. You sum 5, then you get 0. So this is the theorem, the intuition. And it's the same as you change how you start with this, because you start with here, but once you rotate, it becomes 0. Unless that this is always 5, multiple of 5, then you get 5. That's it. Okay. So now I want to show that this map, is unitary. Because it's unitary, so we can do the quantum. We can write it as a quantum circuit, right? Otherwise, that just something. Okay. So how can I prove it's unitary? So in order to prove it's unitary, I need to prove that basically I need to prove that the length is the same. If I start with a vector, here I say if my state psi is x, I say alpha x x. Once I do Q quantum functions on psi, the length is preserved. So that means that if this guy is 1, the length of this guy is 1, then the length of this guy must be 1. Then it's unitary. So the condition for this guy to be 1 is the summation of all this x is 1. So what is this? So I just write the definition. Oh, okay. So once I do quantum Fourier form, I get x, right? I just map x to be this guy. Okay, from 0 to n minus 1, omega n, sk. So this is the this guy. Let's say this guy is 1 for convenience. Maybe I just 5. So what's the length of this guy? Of this vector? I just do the absolute value and square, right? So the coefficient of k is this. So let me just write down, right? The coefficient, I mean, we can do slow. So k is 1 over square root of n, summation x, alpha x. But coefficient of k is just 1 over square root of n, alpha x. Okay, so we are right. Just exchange this double sum. Okay, so let's say this is called yk. So the length of this new vector is just absolute value of yk squared and sum over k. So length. The sum over k from 0 to n minus 1. This guy squared, yk squared, which is 1 over n. All right, so sum over x, alpha x, xk. Now you need to take complex conjugate. So you get y, let's say the summation of y and omega n minus yk. Because you complex conjugate. Right? And you get alpha 1. Right? Okay, so finally you get 1 over n summation of x and y omega n. Now that's the omega n. Now this x minus yk alpha y. Oh, alpha x alpha y. Alpha x. And the summation over k is here. So we got three summation. One is k, one is x, one is y, and then omega n x minus y times k alpha x alpha y. You can just if you this proof is somehow a little bit tedious. Okay, so now I can change the summation. I change x and y here and then do the k. I just sum over k first. So I change x summation of x and y. And let's see this guy. So this guy is what? This guy is omega n k times some number x minus y. Okay. So now the previous identity tell me that this guy is non-zero if only if x minus y is multiple of k. But x and y are from 0 to n minus 1. So if this guy is non-zero, if only if x minus y is multiple of n, the previous identity. But x and y are from 0 to n minus 1. So the only way for x minus y is a multiple of n is x equals to 1. Because x and y are from 0 to n minus 1. How can x minus y multiple of n is only x and y are the same. So that means that I can these guys n times iota of x y. Right? So n delta x equals y. Now, since it's delta, right? So double summation of x and y collapse into single x. And n and capital N cancel, so you get summation of alpha x squared, which is 1. Finish it. That's all. So this is just exercise on a textbook, but I try to write down because I think every.
So can you remind me on what I think you already told that what is the basis state?
Just a 0, 1 state. Or the states can be written as a bit strings 0, 0, 0, 0, 0, 1.
Okay, so it's not some complex.
It's not a complex state. Yeah. So
it's not an entangled state.
Yeah, not entangled. Okay. So where I define so this is a simple form because in order to specify a linear transformation, I just need to specify how it acts on the basis state. So any state can be written as summation of this guy. So when I say that, so when I try to compute the quantum function transformation on this guy, I just compute it on the basis states and then connect it. Yeah, this is the definition. Yeah. So I write this because this formula is easy to remember compared to the previous one. This guy is easy to remember. You just need to remember that you put whatever number it is on the exponential and change it to another.
Yeah.
This is similar as the first transformation. You just put your f of t and then f of t and you put exponential omega t. And what is proof is that this guy is unitary. Yeah. Because of that is so that means that this guy can be in principle efficient prepared by using the standard quantum circuit. Okay, so yeah, so this is the proof. Okay, so the end of this week is I will tell you that if you have big quantum function form, then you can find a period. This is the okay. Before we talk about this, let me just recall the Simon's algorithm. Because the Shor's algorithm, what Peter Shor come up with this Shor's algorithm because I think this is what he said is that he's inspired by his previous Simon's algorithm. Okay. So just let me recall it. So Simon's algorithm say there's a Boolean function, and promise there is a secret S, which is a non-zero vector, such that f of x equals to f of y if only x equals to y plus x. And the goal is for you to find S. And this is a so-called matching problem, right? Because in order to find S, you basically need to find a collision. So basically, perfect match. You need to find the perfect match you need to find a pair. Okay? So each x is one partner y, where f of x equals to fy. Basically, f is 2-to-1 function, and then for the test, you basically find a pair. If you find x and y, such that where f of x equals to fy, then you just use x plus y, give you s.
So once more, why does m need to be much bigger than m?
Yeah, it's actually you can do the same.
The same is fine because I could even do m is n minus 1. Because it's 2-to-1.
Yeah, sure.
So,
but it's still large. Okay, basically, yeah.
Yeah.
The complexity is I think it does not change the difficulty of this problem.
No, okay, but why does it say m is much bigger than m? What's the reason?
I think
because it's not really needed, right?
Yeah, it's not really needed. Yeah.
So why?
I think it's fine. I think it's fine that m is just the order of n.
Okay.
M minus because it doesn't change the hardness, right? Hardness basically comes from that there is exponentially number of pairs. So even like if you x, it's hard to find the y. That's the answer.
Yeah.
So yeah, this is one. Yeah, actually, this example shows the other thing. For example, this is an example that I showed you. So what's S here? just easy to check, right? You say, oh, 0, 0, 0 has output 1, 0, 1. We'll just find a pair, right? Pair is 1, 1, 0. So S is 1. And you are told it's simple one. Let's say you have 1,000 bits. Then you cannot check one by this truth table, right? And the lower bound is square root of 2 to the n. And remember, this is the common circuit. I think I explained in the video, but let me just quickly go through it. You start with all the 0, 0, 0, 0, and you apply Hardeman gate. And you compare Hardeman, you get. Okay, so basically, Hardeman to the power n gives you all the superposition of it. So Pn is a set of NB string, right? You get a set of NB string X and the somewhere one string. This is the states before I go into this unit or this oracle, which encodes F. Okay, so once you compute this, now you go through the UF, right? So you compute X and then store it into the previous X. So this is the state before I go into the next Hardeman. Okay. Now, once I get another Hardeman recall, so remember there's an identity when X becomes Y and minus 1 to X dot Y and then this. So this is the state, final state before I do the measurement. So now I do the measurement on these two parts, on this state. Okay, so let's say I measure the second half QB first. So I try to make, so this is the formula. I try to measure this guy first, f of x. Now, whenever I measure, I get something that says W. So now f of x is, somehow I fix this guy to be W. But how many x push these to f of x equals to W? We have two of them. One is x, one is its partner. And its partner is basically x plus s, or secret s. Definition. So whatever it is, this guy is W, the previous will be summation y, because y is not affected by x. Right? Minus 1 x dot y plus exactly the same expression, but x has a partner, which is x plus s dot y.
So is Pn
set of NB string.
okay?
Yeah.
Set of NB strings.
So P2 is only 0, 1, 0, 0, 0, 1, 1, 0, 1, 1.
Okay.
P string and theta.
So it is n bits.
Yeah, NB string.
X and Y are both
NB strings. Yeah, sum of NB strings. All the possible. So X has 2 to the n different possibilities. Y is also 2 to the n different.
And we sum over all.
Yeah. So this stage is very complicated. Now you measure the second one. You will get something. You collect something.
Okay.
By
So
quantum mechanics.
we only take the function of the x and we export it with the y.
Right. This is the states. Now you do the measurement. You measure our second half units. Now you will collapse. I mean, you cannot control which state collapse, but you collapse with some W. Right.
Okay. And why do we have the minus 1 to the power of x times y?
Oh, this is the formula that here. This is because these states, this Hardeman tensor n acting on x will give you this. This is the formula maybe here. So when you apply Hardeman on x, you will get 1 over square root of 2 to the n summation y minus 1 x dot y. This one.
Okay.
I think this is as I proved in the video. Or you can just remember it. It definitely. Right. So this is the state. After this is the final state before you do the measurement.
Okay, this makes sense.
Right.
So 1 over 2 to the power of 1.
Right.
Minus 4 1.
Yeah.
I mean it makes sense. Yeah.
Okay. So now if this is the final, right? I measure the second half qubit, right? then I will guess I will collect this guy. I don't know which one he collects, but let's say W. Basically, then that means that I will fix x. I will fix x such that f of x equals to W. But there are two of them. It's x and its partner. And its partner is x plus s, secret s. So that means that it's x. Can either be x or x plus s. But there are two possibilities. Because I fix x, then there are two of them. Right, so because there are some normalization becomes quite fun because you just need to know that it collapses to fix x. Okay, so you got two of it, right? You get these two expressions. Now I think the proof is very simple. You just collect, you just see, this is constant, and then summation y is the same. So you just pull out, and you say minus, you got this summation y, right? So you just pull this guy out. Sorry, this is yeah, pretty cute. However, you can take out one of minus one x dot y, then you get 1 plus minus one x dot y. Just for this that's going to be same. These are the other same, this x dot y. So you guys, now you can make what? Now you can measure the first two. You can measure the first two. You measure the first n qubit, then you get some outcome y. But what does y tell us? The coefficient of y is 1 plus minus y minus 1 to s dot y. But s dot y is either 0 or 1. Right? So if you get some y, this y must satisfy this relation. Minus 1 to s dot y is 0. If it's 1, then you get 1 plus minus 1 is 0, you cannot measure. There's no such one. So if you get some y, then you get the vector y, which is somehow like normal to s. So you get some information of s, right? So y is normal to s. So you can do it more times. Maybe you get some y, you just run a circuit, you get some y1 normal to s, you get some y2 normal to s, you get some y3 normal to s. And you get n minus 1 normal to s. Now you have a vector, for example, in 3 dimensions, you have a, if you know your vector is normal to 2 independent vector, then you almost determine this vector. Right? So if you, in n-dimensional space, if your vector is also normal to n minus 1 guy, then you determine s. You just solve a linear equation. So each measure gives you y where it's normal, then your collection of n minus 1 independent of y. Suppose you are lucky, right? Then basically, if you have n minus 1 independent of y, then from a system of n minus 1 linear equation, then y is unique, then s is uniquely determined.
As long as it's normalized.
Huh?
As long as it's normalized.
Right, but now we are in the 0, 1 bit vector. So there's only one of them. There's only fixed one, right?
Oh, okay.
Yeah. So this is the trick. Okay. And then one can prove that this algorithm success is, you can say, oh, you might say, oh, it's 28%, right? It's not large, but you can do that 10 times. Then you become 99%. So you spend that. So notice that you only spend like n different measurements, right? Even you run this algorithm for 10 times, you spend only 10 times small n, which is much less than the square root of totally. Right, so this is why I explained before. Right, so this algorithm success rate is close to like 28. I say greater than 25. So you may say, oh, it's bad, right? But this algorithm failed. But this means that this algorithm fails at most 75%. Right, so that means that how about you run this algorithm 10 times? Then all of them fail at most 0.75 to the power 10, or 0.05. So this algorithm, if you spend 10 times algorithm, 10 times n on this algorithm, the successful rate is at least 95%. And you only spend 10n, right? So 10n is much smaller than the lower bound for classical. Classical lower bound is 2 to the n divided by 2. So this is the somehow state of the art of the so-called Simon's algorithm. Let me see. Oh, okay. Okay, so now give you the final part. The final part is that this is the Shor's algorithm, very a little bit complicated. So we need to do the similar thing. Let's see how should I say it? Okay, so let me explain. So now we want to use suppose that we can do this final version. Now I will claim that you can do this, then you can find a vector. You can find the order. Okay, so first we do the same thing, right? We pick, let's say you want vector number n. Now you can pick large enough. You pick number of qubits such that 2 to the n is larger than n, because you need to store enough information. This is simple. You just take the log of 2, then you get number of 2. Now suppose you add so-called and you create auto superposition. Now you apply so-called control unitary. Simply speaking, you need to do the a to the x. Basically, let's say the base state x, you do the a to the x mod n. Okay, so I will explain why this can be done. But let's say suppose this can be done, and then you run and you follow the Simon's algorithm. You just measure the second register. Then you apply the Fourier transform. And then you measure the first register. Then finish. And suppose the order of I is power of 2. Then you can find the order. You might say, oh, okay, so this is the process. So let me it's a little bit complicated. So let's be slow. Oh, so this is just because I find that it's very difficult to write on the board. So let me explain. Okay, so let's compare to these assignments, right? So remember that before we do this Simon's algorithm, before we go into the Lisa, we have the state looks like this. This is a state which we have x and f of x and the collection of all possible x and some normalization. This is x f of x before we go into the Lisa. So in order to do it in Shor's algorithm, do the factoring, we just need to change f to be a periodic function, which is a to the x, because we need to find the period of function, right? So so simply speaking, you just run this algorithm and change your f to be a to the x, not a. This is
okay. So the UF is simply the operator representing the function.
Yeah, exactly. Just compute x and store it.
Yeah.
Okay, so if you think this is true, then you can skip everything and go to here. Let's see. Oh, sorry, I try to put it down for so so this is, let's say this is the initial state you have. This is similar to Simon's algorithm, right? You have some auto superposition x, which you can do it. Now you put it in f. Now let's say forget about this normalization, you get x and a to the x mod n. You just compute f of x and store in the second qubit. But now f of x is just some a, which is a number you just randomly pick, and you want to find the order of a. So you just compute f of x. Now f of x is a to the x mod n. So this, up to this stage is similar as the Simon's algorithm. Okay, so now you can follow the Simon's algorithm, right? You measure this down. You measure it. And whatever it is, right? Whatever it is. For example, what do you mean? So you get x and a to the x mod n. This is the state, right? Summation of x. And you measure this. And whatever you measure, right? W something. But this is a period function. So this x will contain now have the period information of this. for example, let's say x a let's say a to the x0 is w mod n. Then the next one will be a to the x0 plus r, because it's only w mod n. Right? And the next will be x0 plus 2r. So you will get the superposition of all this. So once you do this, you'll get something. This is still w. You'll get something, for example, you get that with some x0 and x0 plus r and x0 plus 2r. Right? Because all this, well, this guy has the w. Right? Yes.
So aren't there other, I mean, you're saying W, but there are also other values, right? That you can get from the.
Yeah, but you cannot control which W it is. You just measure, because in quantum, right? You just measure, you get some W. You don't know which W it is, and you know which W it is, but once you get it, you know whatever state it is. You don't know this guy, right? But you know the state must looks like this, with some period information R sit inside this state. So you get some x0 plus jr, where j from sum to 0, sum from 0, x0 plus, let's say suppose r to the power of 2 for convenience. So it's 2 to n divided by r minus 1. This is the number of period in this, because basically you start with x0, right? The gap is r. And then the density is total 2 to n. So if r is a power of 2, then it's divisible. You still get 2 to n minus r minus 1 x0 plus jr. Now you use a quantum Fourier transform. Oh, hopefully I didn't. So remember quantum Fourier transform did is that you will put this guy onto exponential and add it with another variable. So let's say this is k. So you get k from 0 to 2 to the minus 1, this guy, x0 omega n x0 plus jr times k. We just put this guy on the exponential and with extra variable k, then you sum over k, and which is nu, capital N to the unit. Okay. Up here. Good. Okay, so we just pull out this omega n to x0 and exchange the sum. So k from 0 to 2 to the minus 1 and sum over j to 0 to the minus r divided by r minus 1 and this. So this is omega n j r k. I actually put this, but because it's very complicated, so I just do it on PowerPoint. I mean, the proof you can see the textbook, but textbook has spent like 100 pages. So I need to like extract the idea. Okay. Okay, very bad. Okay. So now notice that this n is not the number I need factor. This n is 2 to the something I pick. Because so now I just write down the sum. So what's the probability that I may now I can measure the first hand. What's the probability I get k? Is this guy squared? Oh, so it's these guys. This guy, j from 0 to the minus divided by r minus 1 is omega. Now I write capital N to the n j r k squared. This is the probability I measure k. Is this guy. Good. Now I write definition. Omega, the 2 to the n to the unit is exponential 2 pi I divided by 2 to the n. So it's 2 pi I j r k divided by 2 to the n is sum of j to 0 and then 2 to the n divided by r minus 1. So it's this. Now I divide it. So notice that r is the guy I want to know. So I divide r, numerator and denominator. So I get from j to 0 to the n minus 1 divided by r minus 1 is going to 2 pi I j k divided by 2 to the n divided by r. So now this guy equal to this guy. This guy is it's not now this guy is 2 to the n divided by r root of unity. So I change that omega to the divided by r unity with jk sum over j is 0 and 2 to the divided by r minus. So you see this expression is the power is the omega is the sum of omega power. So this guy is non-zero if and only if k is multiple of 2 to the n divided by r. So once you measure k, whatever you know is that k is some integer multiple of 2 to the n divided by r. Now the goal is for you to find r. Right. Now so the rest is very simple. Suppose I get k1, k2, right? So I know that each k is integer multiple of 2 to the n divided by r. Let's say this is alpha. Let's say this number is alpha. So for example, I'm gonna get 2 alpha, 5 alpha, 7 alpha, or whatever alpha. But if I get 2 alpha and 5 alpha, then I compute the greatest common divisor, I will get alpha. Because 2 and 5 are over. And once I know alpha, then I can compute r. Because I know alpha is 2 to the n divided by r. So I get the order. Then I can once I get this r, then I can put back in the Shor's algorithm and find the order. And find the prime factor. Since now I can find order. Oh, so this is the Shor's algorithm. Basically the main algorithm. There are some technical details. So for example, in order for this algorithm to work, you need to find you need to find multiple, right, such that these two are coprime. If this number are not coprime, for example, 2 alpha and 4 alpha, then you get it wrong. You get it right. So what's the probability that 2 random chosen integers are coprime? So this is right. You need to solve this, right, so that you can prove that this previous algorithm work. What's the probability? You that 2 random chosen integers are. Right. Nice. This is the answer is done by like Euler. So 6 divided by pi squared, which is about 71%, 61%. So it's very large. Oh, so is this? Oh, so if you believe this, then nice. Then it shows algorithm work because it's argued that. Thanks to Euler. Okay. Okay. So final. So the next 10 minutes, I will prove this. I will prove why this is. This is just for fun. But 6 divided by pi.
So it's accidentally the sum of one.
Yeah.
Like the 1 over
n squared.
n squared.
Yeah. Exactly.
Okay.
So this is this is just for fun. I did just tell you that this Shor's algorithm. Yeah. Once you this tell that this you get very basically you have very high probability that 2 numbers are. But the proof basically very simple. So yeah, as you say, right? So suppose you know that this is true. And so to prove this, you need to do yourself for analysis or whatever. So in order to you randomly pick 2 numbers, right? In order to make sure that these 2 are coprime, basically first is the first condition is they cannot be both even, otherwise they have the 2, right? So what's the probability that 2 numbers are odds? Is half times half, because the first number needs to be odds and the second number will be odd. So it's 1, 4, right? So it's 1 minus. So they cannot both divided by 2. But what's the probability that they are not both divided? It's 1 minus 1 divided by 4. Because basically it's 1 minus 1 divided by 2 squared. Because because the probability they are both even is one divided by 4, and they are not is 1 minus. And similarly, they cannot be both divisible by 3. So so simply speaking, the probability that two numbers are for prime is basically 1 minus 1 divided by 4 times 1 minus 1 divided by 9 times 1 minus 1 divided by 25, right? Because not divisible by 5 or is right.
What happened to 1/16?
Oh no, because if yeah, already in 2. Yeah. So this is all the product of all the prime. Let me use p. So it's 1 minus 1 divided by p. Use the product of all the primes such the product of all the primes that 1 minus 1 divided by p squared. So my question is that what's this? And this is back to Riemann that this guy is indeed the inverse of each guy. Oh, so proof is, let me just expand this. All right, so you remember this. So now we start with this and use that is. So each number n has a unique prime factorization. Right. So I can write this guy in terms of 1 plus this guy. Right. Because each integer n has unique prime factorization. So I can connect the power of 2 squared and the power of 3 squared, power of 5 squared. For example, 1/6 squared is the product of 1/2 squared times 1/3 squared in this expansion. So these are infinite expansion, infinite products. Okay. So this is the product of primes 1 plus power of p squared and 1/p to the 4th, and 1/p to the 6th, all those product primes. Okay. Now this guy is geometry series. I mean I can compute, right? So it's sum over product primes 1 minus p squared. That's it. So this is back to the Riemann. I think at that time that people already know that. So you can see there's all the mystery comes from this formula. Is that somehow like if you can understand the 1/n to the s for arbitrary s for this behavior of this zeta function, then you get a lot of information on price. So this is the techniques between someone connect. Someone if I want to know the collection of behavioral price, I can use this 1/n. I can use this kind of I can collect into zeta function. Okay, so this is just for today. And so what's the remaining? The remaining is that I tell you the quantum Fourier transformation can let you find the order of given integer. Then you can use this to do the prime factorization. And once you have factor integer, then you can break RSA. So this is the whole logic. But there's one remaining thing is that I'm not what's the effective way to do this quantum Fourier transform? Because this algorithm, the most important part is that, I start with this, then you can use a social parameter Fourier transform, you get this. But what's the efficient circuit for you to start from here to here? Once you have this, then everything just follows. So yeah, so next week I will just use the first 30 minutes and explain I use first 30 minutes and tell you how to construct this quantum Fourier transform. Then basically we finish this short algorithm. Yeah, that's it. Oh, see you next week.